to the cloud. So linearization objective, write a linearization model for a given function and use to approximate values. Right. The first part of that objective doesn't really tell us too much. It's like, okay, learn about the thing that is the title of the lesson, but use to approximate values. That's going to be more important. And you can see, pretty classic examples below. Determine the linear approximation model for this function at x equals 8. That's all well and good. But after that, it says, then use the model to approximate the value of the cube root of 8.05 and the cube root of 25. The idea is that we can use derivatives to make approximations of functions, and those functions or those approximations could have meaning, right? And if they do, then we can use those approximations in lieu of the exact values, right? So you can see the whole blurb here, but I'm just going to kind of walk you through it real quick because, the notes here are wonderful, I think, because I typed it all up myself. Although the format of the font and everything is disgusting. But let me show you on Desmos really what I'm talking about here. And actually, a lot of this stuff, before I clear it all out, a lot of this stuff is kind of based off what I just did here. Quick double check. I'm pretty sure I have a linearization calculator up on Blackboard. I'm just looking at that real quick. Oh, I have differentials. I do not have linearization. Okay. I will make sure that there's a linearization calculator on Desmos or on Blackboard before the evening's over. Right? And it'll be based off of this. All right. So let's say we have a function, and this function is as good as any with some point x comma y, a comma f of a. All right. So I'm going to get rid of this table because I don't need that. All right. What we're going to do is find the derivative at a. But when you find the derivative in the point slope form to write the equation of a linear function, it takes on a kind of a new form. So we have y equals, and I don't know, I meant to change this. It's really m times x minus x sub 1 plus y sub 1. That's the better form. That's the point slope form of a linear equation. That m is a slope, and we've learned throughout the last couple of units that a derivative is an instantaneous slope, right? So what we're looking to find here is the slope of a tangent line, right? So the slope of the tangent line would be the derivative at some point along the curve, right? So if we're saying y is equal to some function f of x, and there's some point with an a value, that point would correspond, or that x value would correspond with a y value of f of a. I would have these two ingredients here. This would be a, this would be f of a. With m being the derivative at that point, right? The derivative of the function f of x at a would be f prime of a. So instead of saying y equals, they tend to say let it be L of x, just because L stands for linearization, the linearization model. But it could be y equals mx plus b, it could be y equals ax squared plus bx plus c. But once you start giving it a particular definition or meaning, you tend to kind of port over the notation for that. So if we're talking about position functions, yeah, we could say y equals, but it's better to say s of t. So for the same reason, we would call this L of x, right? So it's really y, but y equals L of x, making this L of x, right? So that's where the notational comes from. But the reason I'm bringing that up is because we have all this stuff ready-made to go into Desmos. All I'd have to do to write a tangent equation is, well, whatever notation you like, but they're using L. So L of x would be equal to f prime of a times x minus a plus f of a. All right, so I'll give this a different color. I should give it a little, make it a little thicker. I'll make it red. And so that's my tangent. And depending on where I go around that curve, you can see that that tangent adjusts accordingly. All right. Now, if you want to get, get fancy, you just type in tangent. And it's a tangent line. Actually, let's see here. You can hide the point and then do it like this. Looks kind of cool. Actually, even better. Maybe, yeah, that's a good place to put it. Yeah, there we go. We got that tangent line. All right, but it's also the linearization model. All right, so if I need to make an approximation, I can use the line instead of the curve. All right, now depending on the nature of the function, it may not be necessary, but in the case of, some really complicated looking functions, you might want to go with a line as opposed to a more, like I said, complicated function. All right, so I'll just zoom out here a little bit just so you can really get the point, but you see that tangent line. And now if you go out for that took off on me. If you go out for large values of x here, you can see the behavior. I'll get this up to like 50, I guess. You can see that the behavior of the tangent line is very much the same as the line or as the curve itself, right? So you'd have some variation, but nothing too crazy. So we'd actually get some pretty decent approximations just by using the tangent line, right? So I'm actually going to make up an example here because a little bit of a precursor based off of what I just did with Desmos is kind of in order here. So let me do, you don't know where to put it. There's really no good place. I'll steal some room on the previous page. So let's say we have example, use linear approximation to find the value of, let's say, the square root of 10 at 26. So use linear approximation to find the value of the square root of 26. It's really, I didn't want to use the word approximate again, but it's really using the technique of linear approximation to find the approximate value of radical 26, but it's a lot of approximation in one sentence, so I shied away from it. But what we would do here is we would write a function that represents this, right? So that function would be f of x is equal to the square root of x, which is what we have in Desmos, which is good. That's the whole point, right? So then what we would do is choose an x value that's near 26. All right, so choose a convenient x value near 26. All right, and by convenient, I mean convenient to the function that we just wrote, right? Because if x is equal, and just kind of talk this out real quick, if x is equal to 26, then f of x would be exactly what we're looking for, right? So it's kind of like we're unsubstituting. If you really think about it, like you're evaluating a function we're unevaluating the function, right? So this was, I'll even pull it back a step. This was f of 26 is equal to radical 26. All right, but that got us nowhere. We don't know that, right? I mean, a calculator does, but we're pretending that we don't have calculators for some reason, even though I'm using a calculator to demonstrate all this. So what we do is we back up a step and we say, okay, well, what was it before the 26 was plugged in? It was the square root of some variable. That variable is typically an x. I mean, so f of x instead of f of 26 becomes radical x instead of the radical 26. So we're going to go back a step and say, all right, well, let's choose a value close to 26, but a better value, more convenient value, right? So at x equals 25, that's nice and convenient for a function where we're looking at a square root. A perfect square is a nice convenient value, right? So to write our linearized model, we would need our derivative, right? So this is the same as saying x to the 1/2 power. I'll just kind of smidge that over and throw that in there. So that's 1/2 x to the negative 1/2, which is the same as saying 1/2 radical x. Right? Negative exponent, you bring it down to the bottom of the fraction because it's a 1/2 power, that's the same as the square root. Right? So I need two pieces of information. I need f of 25 and I need f prime of 25. So the f of 25 is what you would get if you take that 25 and plug it into the original, quote unquote, original function, and that'll give you a result of 5. Right? Then f prime of 25 is what you would get if you took that 25 and plugged it into my derivative function. Still involving the square root of 25, which is 5, but this simplifies down to 1/10. So my L of x is going to involve all these ingredients. So L of x is equal to f prime of quote unquote a, some number that we're deciding upon. So this is some value that we'll call a. So f prime of a is 1/10, x minus 25 plus 5. All right. The whole idea here is to write a tangent line equation at this point, because now what I can do is, instead of evaluating my original function with a 26, which I couldn't do because I don't know the square root of 26 in decimal form, what I can do instead is evaluate this much simpler looking equation, or simpler equation period, with that 26. All right, so then I could find L of 26, which would be 1/10 times 26 minus 25 plus 5. All right, so 26 minus 25 is 1. 1 times 1/10 is 1/10 plus 5 is 5 and 1/10. So 5.1. All right. Now, if you just rough out the square root of 26, you see that that's what it would round to, 5.1. And that's because 26 is very close to 25. And what we did, and I can show you here on Desmos, is we took a nice convenient value, 25. We wrote a tangent line equation. Now, evaluating my original function, f of 26, again, funky decimal, but as a coordinate, it would put it at a point that's pretty close to the tangent. All right, the tangent again is at 25. 26 is just a smidge to the right of that, right? You can see here, I mean, maybe you can't. I'll turn off my tangent line equation, and then turn it back on. You can see that there is not much of a difference between my tangent line equation. In fact, they're indistinguishable, and the original function at this location. So I could have found a reasonable approximation of the square root of 30. Let's see, with this tangent line, square root of 40 even, but then it starts pulling away. At 45, I'd have a little bit more deviation because the tangent line it's going off on a tangent. You know, it's deviating substantially now, and maybe that's too much, I don't know. But 50, 55, 60, I'm losing the accuracy of my approximation the further away I get from that point of tangency. So if I went to use this technique to find the square root of 125, I'm probably not going to get a good approximation. However, instead of working with that x value of 25, I could just move my tangent line over, right? My point of tangency over closer to that point and just do the process again, right? The whole idea is that the closer you are to the point of tangency, the more reasonable or more accurate the approximation should be. And the benefit of stuff like this is, I mean, aside from, you know, simple applications where it's like, if I just want to do a computation in my head, there are other applications. I mean, I actually use this technique in my high school algebra classes, because what they need to do is I have these Sphero robots, and I use the robots and coding in order to demonstrate motion and stuff like that, velocity, acceleration, all that good stuff. But the thing is, I can't tell the students, right, graph this along the path of a third degree polynomial, because it's, you know, freshman algebra class. So what I can do is I can linearize the third degree polynomial and give them headings that are linear. Also, it's much easier to code in linear movements, right? Especially with a Sphero, because Sphero is like aim this way and go for this amount of time, right? So, and that angle, the angle of the heading is dictated based off a linear movement. Okay, so being able to translate from something that is non-linear to something that is linear is kind of important. Right? Let me just save this real quick. Linear approximation. I could actually show you Sphero heading angle. I did a circular. Is that the? Yeah, I guess it's fine. But you see here, so in order to create the heading angle, what I actually did, I had to give them this information. Like I wanted them to do it in a circular pattern, a circular movement based off of a different, differing radii, and have the Desmos report out the angle. So what I did was I had to do an inverse tangent on the slope, which gave an angular measurement, right? But that inverse tangent on the slope came from the function itself, which I linearized using this very process. You see f prime of, I use c instead of a, but f prime of c times x minus c, and off the screen there is plus f of c. Okay? And then I had to put some other parameters in there to kind of get it to stick within the, I mean, it was involved, but the heart of the whole process was the linearization model. So, that was actually pretty nice application of this, but that's just a little taste of it anyway. You know what? I appreciate that, but I gotta tell you that the freshmen aren't really appreciating it too much right now, because they think I'm making everything unnecessarily difficult, and they also think that that I'm taking anything that could be possibly fun and then ruining it with the math. But it is what it is. Can you explain the top page part of linear approximation? Where'd you get the 26 in the equations? Oh, the 26. That I was a made up example. All right, so like I made up the example, use linear approximation to find the value of radical 26. All right, and so f of 26 would then be equal to radical 26 by definition. So if I were to say something like, for example, find, I don't know. I'm going to do a trig one in a couple of minutes, so I'll stay away from that. But let me say, I'll do a log. Let's say I needed to find like the natural log of 4, right? If I needed to find the natural log of 4 by approximation, one thing that I could say is that f of x, well, even before that, f of 4 is equal to the natural log of 4, right? Where f of x is the natural log of x. So I'm unevaluating the function, right? So now I kind of feel like maybe I should do this example because I took some time to think about it. It's a good way. I mean, it's not anything that we weren't going to cover anyway. I don't want anybody to be like, "Oh, thanks a lot for asking the question. Now we're going to do another problem." So let's say approximate the natural log of 4. Right. So it's the same idea. Right. We start off with some given expression, ln of 4. I don't know the answer to that. All right. So what we got to kind of imagine that we were, just going back to an algebra 2 class or college algebra or pre-calc, whatever. What this was originally, they gave us f of x is equal to ln of x. And then they said, find f of 4. Right. From there, we then had to replace the x with a 4 and simplify. And then we got to this ln of 4, and I don't know the answer. Right. So what we're going to do is we're going to say, okay, forget that. We're going to go back to the original function that brought us to the ln of 4 and choose a more convenient value for x. All right. So what do we think about in terms of convenient values of x when it comes to a natural log function? Right. That's the tricky part. Right. So what I can do is I can go back to my linear approximation Desmos. I'll put in ln of x. All right. I mean, it'll give you a good look at what a tangent line's behavior would be. And you can see very much like a root function, it's going to be a pretty good approximation. The tangent line will be a pretty good approximation for the natural log function. So this is a good license to use this technique to find an approximation. However, when we're thinking of just a natural log function, just in a vacuum, we would be saying, all right, what are some nice numbers that if we were to substitute into a log, like I would choose to do that, so 1's a nice number. 1 gives you a 0, right? So that would be pretty good. But the other nice numbers actually don't show up in the table because E is a really nice number when it comes to a natural log, right? So for example, if I find the log of E, ln of E, result is 1, right? But powers of E are really nice too because of the power rule for logarithms. You remember the exponent jumps over the log? So ln of E squared is the same as 2 times ln of E. They amount to the same thing. So powers of E are pretty good too. So what I would want to do is find a nice power of E that gets me pretty close to 4. right? So then I would be thinking, all right, well, what do I got for powers of e? E to the, well, e just in and of itself is 2.7-ish. E squared is too big. So I'd probably want something in between e and e to the second. So maybe e to the 1.5. That's not too bad. I mean, if we start going too crazy with decimals, then what'll end up happening is we'll make things overly complicated. And then we start thinking about, okay, well, this defeats the purpose of using an approximation technique, right? But e to the 3/2 isn't really too bad. 4.4, maybe you want to kind of play it safer. I don't know. I don't think that's much better, but you might look at that and say, well, that's a little nicer. I don't know. I don't think it is. Yeah, they're both about equidistant away. So I'd rather go with this one's cleaner number. So where x is equal to e to the 3/2 power. All right. So this is a nice number near 4. All right. A nice number near 4. That's all we were looking for. All right. That's where the 25 came from here. It was a nice number near 26. All right. So then we get into the derivative process. F prime of x, 1 over x. So then I would need f of e to the 3/2 and f prime of e to the 3/2. So we're coming up with the tangent line equation, right? One of these gives us the y value that goes along with the x that we just decided on. The other gives us the slope at that location, all right? If I plug this into the original function, ln of e to the 3/2 is just 3/2. F prime, I'm plugging in an e to the 3/2 for x. So that's just 1 over e to the 3/2. All right, so still pretty clean. I mean, pretty clean being a relative term, but it's not terrible. So I have my 3 ingredients. I have my x, the corresponding value of y, and the slope. So my linearization model, L of x, would be, again, just following this form, slope. So 1 over e to the 3/2, x minus the a value. Okay, we call this a. E to the 3/2 plus 3/2. All right. Now our linearization is going to be, I mean, sometimes you're not going to get a clean number. I mean, we got 5.1 for the last one. That was pretty nice. Yeah, you might get an answer in terms of e. That's okay. All right. So I'm going to evaluate this by saying what's L of 4. All right, because now instead of substituting the 4 into the original natural log function, which we didn't know the answer to, we can substitute it into the linearized model and get a different sort of approximation of it. Right? Now, sometimes you end up with something that looks a little messier than what you would begin with, but it's really the skill that we're working on here. And also, full disclosure, as you know, I just made this up off the top of my head, so it's not the best example in the world, but it gets the job done. 1 over e to the 3/2 times 4 minus e to the 3/2 plus 3/2. You could actually distribute if you want, okay, in which case you get 4 over e to the 3/2 minus 1 plus 3/2, which would be equal to 4 over e to the 3/2. And that would be plus 1/2. So this would be our quote unquote approximation. If we wanted a decimal value, you know, it's kind of a paradox, maybe. Not really, I guess, but you know, it's sort of like a contradiction of terms in that if I want a decimal value, I'd have to put this into the calculator, but if I put this into the calculator, doesn't that mean I could have just put the natural log of 4 into the calculator? And if so, why even do this? You know, so at this point, it's really just a practicing of skills. But we can verify using Desmos. All right, so we take a look. We have natural log. We chose as our convenient value e to the 3/2. So I'd put that in as my a value. So e raised to the 3/2. All right, so that's where my tangent line would be. And around that location, it does look like it's a pretty good approximation, at least for a pretty good stretch, you know, from about 3.5 to a little bit more than 5. We'd have some values that could be reasonably approximated by this a value that we selected, e to the 3/2. Right? But we can evaluate our original function at 4 and evaluate our linearized model at 4 and see that they're pretty spot on in terms of approximate values. Right, 1.386 versus 1.393, not too far off. Right, so that's pretty good. All right. Well, honestly, it's very good for a problem I just made up on the fly. All right, but you know, it is what it is. So the problem that I never did because I did these two involves a cube root. But it's really the same skill. The first step in these kind of problems is really just the setup of the function, right? The idea of unevaluating the function, right? So looking at number 1, now they told us flat out, they said, all right, we got f of x is equal to the cube root of x. But if we're looking to find the cube root of 8.05, what that's saying is that f of 8.05 is equal to that expression. Some function evaluated for when x is equal to 8.05 was equal to the cube root of 8.05, which means that the function itself must have been the cube root of x. So instead of working with the 8.05, what we're saying is let's get a nice value near 8.05. So that nice value is a. So we would let x equal to the be equal to the 8, which is really where the framework of this example comes from. All right. So going into this, you know, it's the same idea as the first one that we did. X to the 1/3 is what my original function would be. The derivative of that, 1/3 x to the negative 2/3. All right. And so evaluating this function for our nice value of 8 and evaluating the derivative for that nice value gives us, so f of 8 would be equal to the cube root of 8, which is 2, and f prime of 8 would be 1 over 3x to the 2/3. So that's what this is equivalent to, 1 over 3x to the 2/3. But that would be 1 over 3 times 8 to the 2/3. 8 to the 2/3, cube root of 8 is 2, squared is 4, times 3 is 12, so 1/12. So when we want to linearize here, we have all our ingredients just by following the process. You're just following steps to come up with that if that's all you're worried about. But it's slope x minus your nice value plus the y value corresponding with that nice value, which is 2. All right. So then finding the value of 8.05 and the cube root of 25 is easy. They said that we had to work with this nice value. This nice value is what I meant to circle emphatically. So we're stuck with that 8 for the 25, but it's saying find L of 8.05 and find L of 25. Okay. The 8.05 isn't bad, but like I said, we have this Desmos, so why not use it? I mean, I never said that, but here we are using it. So x to the 1/3 is the original function. We have our linearization model, but we want this to be at not e to the 3/2 like that previous example. Our nice value is 8. So then I would evaluate L of 8.05. If it's willing to give you a fraction answer, take the fraction answer. All right. So 481 over 240. Just so you don't have to worry about rounding and stuff like that. You know, it's a little bit of a convenient approach. All right. If you want to put it in decimal form, just to get an idea of the answer, that's probably not a bad idea either. Or at least visually to inspect, make sure your answer is not absurd. Because we know the cube root of 8 is 2, so cube root of 8.05 should be somewhere close to 2 on the high side. Right? But then L of 25, all right, they're going to give a fraction answer for that too. I'll take it. 41 over 12. The decimal variation on that is about 3.417. Oh, the cube root of 25. Well, it's definitely less than 3 because the cube root of 27 is equal to 3. So this is way off, right? But if you're not sure, 25, raise it to the 1/3 power. Yeah, so 2.1. So this is about half a unit off. Whereas the other one, if it was off, it's not going to be off by a whole heck of a lot, right? So, and the rationale behind that is, I mean, if you look at it, over at 25, the x value of 25, you see a noticeable difference between the tangent line and the curve itself. So the tangent line, yeah, it might still be a reasonable approximation, might not be too terrible, but it's not as good as it was over here. And it's only going to get worse after that, right? One of the challenges that we'll have moving forward is learning what the extent is of the accuracy region, right? So we call it the radius of accuracy. So how far out can you go in each direction before you start losing the accuracy that you would want to have, right? So the last one that we'll do tonight is the sine function. It says f of theta is equal to sine of theta at 0, right? So again, this is really the same as saying, right, if we want to find sine of pi over 4, they're saying that there was some function that was evaluated when theta was equal to pi over 4, and that gave you the sine of pi over 4. But since we don't know that answer, we work backwards and say, okay, forget it, unsubstitute. And we say f of x is equal to the sine of x. All right. Oh, sorry, f of theta. I mean, it really doesn't matter in the grand scheme of things as long as you are consistent with your defined variables, but it says theta right there, so I can't really excuse my way out of this. So the nice value around pi over 4, that, I mean, that could be debatable because some people might look at pi over 4 itself as a nice value. But when we're thinking in terms of nice values, we want a nice clean answer that you would know just by looking at it. Right? So, and maybe that the sine of pi over 4 is equal to radical 2 over 2. But let's just say that you didn't know that, but you do know that the sine of 0 is equal to 0. Right? So that suspend your disbelief for a second. Right? So where theta is equal to 0. Right? So I'd find my derivative, which gives me cosine of theta. I'm going to evaluate my original function. I'm going to evaluate my derivative. My original function would be sine of 0, which is 0. My derivative function cosine 0, which is equal to 1. All right. L of x. Derivative goes in first, 1 times x minus 0 plus the y value corresponding with that x value, which is also 0. This whole thing simplifies down to just an x. And like I'm using x here because that's the linearized model, but it would really morph over to L of theta is equal to theta. All right. So what we would need to do here is evaluate this for pi over 4. Which happens to be pi over 4. All right, so this is actually what the approximation would be, which is kind of interesting. All right, the approximation is pi over 4, but we know that sine of pi over 4 is actually 1/2, radical 2 over 2. So pi over 4 really isn't too far away from 0.7071, which is what radical 2 over 2 is. Right, so you're actually pretty close, but if you go to the original function and make that sine of x, you see that this linearization model has an expiration date, a very quick one, because after you get a little bit away, and let me go from, let's go -3 to 3, just so I'm not scrolling all over the place here. But after you get a little bit away from 0, so I'm right at 0 now, you get a little bit away, that tangent line starts looking awfully different from most of the points along the graph, right? Along this stretch here, there's a significant amount of overlap, right? So I can use over the interval of roughly, this is where it kind of lays nicely, maybe even like 0.3. If the a value is 0.3, it kind of lays on that interval sort of nicely, and so we could get a nice stretch going from about -0.7 to +0.7, because there is symmetry there before it starts starkly deviating. Right. But the thing is, since it's a periodic function, what we just learned is that for any stretch of graph that has the same slope, we can approximate values using this linear equation. And then all we would have to do is come up with another model that would approximate the downward slope. And then we'd have virtually the whole thing, because we know that every other region is really a set of turning points. And so if you know your max and min, then you can come up with approximations just using the linear model, right? And so 2 linear models piecewise with the knowledge of the maxes and mins would be reasonable approximations of a trig function, as long as you know that it's periodic and it repeats over and over again, ad infinitum. But that's a pretty cool relationship, because now what we can do is with certain concessions to inaccuracy, we can get away with using linear equations rather than trig equations. All right. So again, these are all approximations, but they're approximations with a purpose. All right. So let me put some stars on some problems. some juicier ones. I mean, well, really, it's the whole page. We'll crank these out next time. And then we just have to talk about Newton's method and differentials. I mean, it looks like a lot of pages, but it's very quick. Right, a couple of algorithms, and then that's really the unit. Right. So yeah, let me stop the recording.